Hey everyone in Physics 40S Universe. It is Dr. Carroll here with Unit 2, Lecture 2. Unit 2, Lecture 1 was all about projectiles, getting more practice with the kinematic equations in horizontal and vertical fashions. Now we are going to look more deeply at motion in terms of what causes a motion, whether it's projectile or straight line. What causes a motion? That's not kinematics. Don't kinematics yourself. It's not kinematics. It's dynamics. Okay? And that was supposed to be don't kid yourself. That didn't work at all, did it? So, dynamics, Unit 2, Lecture 2. This is around page 12 or so in your booklet. You'll find it. Headline Dynamics. Don't worry about the page numbers. So, dynamics, we're going to look at Newton's three laws of motion. The first law, famous law of inertia, is what it's sometimes known as. Okay, an object at rest will stay at rest. An object in motion will continue to move at a constant velocity unless an unbalanced force acts on it. Okay, so if an object is at rest, it stays at rest. If object in motion, well, it's just going to continue moving unless something acts on it, whether it's friction or wind resistance or a rope on a pulley or a spring or a fan or something like that. Otherwise, it just keeps on going, like the Energizer Bunny. So if at rest V1 is 0, V2 is 0, so the change in velocity is 0, just sitting there. If a cart is moving at 10 meters per second and 20 seconds later it's still moving at 10 meters per second and no unbalanced force has acted upon it, then the change in velocity is 0, so it's in constant motion. However, if the velocities are different, then an unbalanced force has acted upon it. It has accelerated, and here change in velocity is not 0. So that's the first law. And these three laws, if you look at the Flipping Physics, this is our great video series. Flipping Physics talks about Newton's three laws in really fun, good ways. So search on YouTube for Flipping Physics, and you'll find all sorts of good stuff about this. Newton's second law is the famous one. They're all famous. F net equals ma. So the net force is mass times acceleration. So in other words, acceleration is the net force over the mass. Force is in units of newtons. Mass is in units of kilograms. So acceleration is in units of newtons per kilogram, which is also the same. A newton is a kilogram meters per second squared, so divide by kilogram. So acceleration is also units of meters per second squared. The net force, you can have more than one force acting on something. Here's some fancy math for you. The sum from I equals 1 to n of F sub I. So it's F1 plus F2 plus F3 plus dot 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 plus Fn. So that is the net force. You just add up all the forces. Force is a vector, so direction is important. So you have to take that into account when you get the net force. And then the third law, which we don't talk that much about in the course, but if you have an action force, there's an equal and opposite reaction force. So if I push against the wall with my hand, the wall's pushing back on me. And again, Flipping Physics does a really good example of how this all works for the third law. So our main focus is going to be on Newton's second law. And to help with that, we have something that you should remember from your Physics 30 class, which is the free body diagram. FBD is the shorthand symbol for free body diagram. And we can have here, don't worry about the page numbers, we could have a card here, and it's just sitting, and the force of gravity is downwards. Fn is known as the normal force. That's the force perpendicular to the surface. And if the cart is not flying up in the sky or driving down further into the ground, then the normal force and the gravitational forces cancel, and that's okay. Now I said it was I said it wasn't moving, but that's not true. It might be moving. I'm not sure whether it's moving or not. I can have here a accelerating force, so a rope could be pulling this cart to the right, and then there's friction which could be resisting the motion. So that might be happening, and if they're equal to each other, if the accelerating force and friction are the same, then the object will be moving at a constant velocity. Okay, so you'd have to look at the numbers to see that. Notice that in the free body diagrams, the arrows are always pointed away from the system. The system is what I'm circling here, and so you have forces acting on the system, but never have an arrow pointed in towards the system. That's not correct. Have arrows going out from the system. And drawing free body diagrams really helps you to organize what's going on. So it's a good skill to have. And let's look at another example here. Here, suppose you have someone in Winnipeg when it's snowy and that person has a dog sled. So the dogs are pulling the sled, and the person is, let's say, pushing the sled, okay? And then there's friction from the snow, the gravity going down, and the normal force going up. So my x direction is the person who's pushing the sled, the dog who's pulling the sled, but they're both going to the x, and they're fighting friction. So that's my net force in the x direction. In the y direction, I have the normal force and gravity, which here I'm going to assume are equal. So the sled is not flying into the sky. It's not like, who has a sled that flies in the sky? I'm not sure. Maybe you can email me that answer. Okay, here's an example where we have, it's from your mini text. In the website, there's a mini text where I took a few pages, not many, but a few pages from an old book, and that's okay. And so it's from there. So I have here a person in the middle. Okay, is that Malcolm in the middle? I don't know. And that's actually Tarzan in the middle. And Tarzan has a friend, Tarzana, who's pulling Tarzan to the right, while there's a beast, a gorilla, who's pulling Tarzan to the left. So the net force in this free body diagram is, well, Tarzana was pulling at 150 newtons to the east. Be careful, the Newton symbol is N. Some people get that confused with north. But N is for newtons. If I put it in square brackets, then I'm talking about the direction north. So I got 150 east and 180 west. So the net force is 30 newtons to the west. So the acceleration would also be to the west. The acceleration is in the same direction of the force, because the difference is you're just dividing by the mass. So it's force per mass is my acceleration. So 30 divided by 90, so 0.33 meters per second squared to the west. So as long as this battle is going on between Tarzana and the beast, the Tarzan, the system, will be moving west at an acceleration of 0.33 meters per second squared. Notice if Tarzan was more massive, the acceleration would be less. If Tarzan was less massive, the acceleration would be more. Now in the second case here, Tarzana has been working out and is 200 newtons to the east, pull on Tarzan, and the beast has gotten tired, only 90 newtons to the west. So my net force is 200 minus 90, which is 110 newtons going to the east. So that's my net force. My net acceleration is just the net force over the mass. So 110 newtons over 90 kilograms, 1.22 meters per second squared going to the east. So Tarzan is going to the east at that value. Okay. The third example, we have Tarzana moving 150 newtons to the east, and the beast 90 to the west. So my net is in Tarzana's easterly direction, 150 minus 90, 60 newtons to the east. So the acceleration is 60 over 90, 0.67 meters per second squared. Now suppose this process was happening, this would be given 2.7 seconds. This battle was going on. So what would be the final speed of Tarzan? Well, assume Tarzan's initially at rest, and then he's accelerating at 0.67 meters per second squared for 2.7 seconds. So that could cut off. So let's do 0.67 times 2.7. 1.81, I thought that's what it was. 1.81, that's V2. 1.81 meters per second. Okay, that's good. And the displacement from the origin, take the origin is 0, so it's V1 delta T, V1 is 0, plus, so 0 plus 1/2 times 0.67, so 0.5 times 0.67 times 2.7 squared, 2.44. Okay, so delta D is 2.44 meters. So you see how we're still using the kinematic equations, but we use the F equals ma to get the acceleration that we're talking about. Okay, now there's all sorts of different kinds of acceleration. You have to be careful what we're talking about. Here, gravity, yeah, gravity is acceleration, but the normal force is canceling that out. We aren't lifting Tarzan into the air. I mean, that could be another thing, swinging from a vine, but that would be another story. So these are classic examples of Newton's law in one dimension, and you'll get some practice on that soon. But what about Newton's laws in 2 dimensions? So here's an example where I have, suppose I have some kid on a sled, a toboggan. The toboggan's 20 kilograms, the kid's 70 kilograms. So a top view, you have a 90 kilogram system, and you have 2 people pulling the sled. They're using ropes to pull the sled. Okay, person 1 is pulling the sled at a magnitude of 50 newtons, 40 degrees north of east. Okay, and person 2 is situated 25 degrees south of east. Okay, so they're both pulling it, so it makes sense that they're both going to be at the same side of the toboggan. I guess you could have one person pushing and another pulling, but if they're both pulling with ropes, this is a fairly efficient way to do it. So let's get the net force, and from there, let's get the net acceleration. So here I will use a vector collector. And so my F1, my x direction, is going to be 50 cosine of 40 degrees. And my y direction, 50 sine 40 degrees, right? They're both in quadrant 1, so they're both positive. F2 is going to be 60 cosine of 25 degrees. So that's my x component. And then minus 60 sine of 25 degrees. So that is my y component. This is pointed downwards, so that's my y component. So my net force, I'll take F1 plus F2 for my x direction, and I'll get 92.68. F1x plus F2x. And some students, by the way, like to solve the number for 50 cos 40 and write that, then 60 cos 25, write those numbers and then add them together. Others don't. It doesn't matter to me, whatever works for you. The y direction, 50 sine 40 degrees plus negative 60 sine 25 degrees, so that is 6.78. So my x direction, I go 92.68 to the right and 6.78 going up. So taking the Pythagorean theorem, 92.68 squared plus 6.78 squared, get the value, take the square root, 92.93. So my net force is 92.93 newtons east, 4.18 degrees north. Okay, so it's pretty close to just having that toboggan going straight across. Just a bit of a turn there, 4.18 degrees, a bit of a veering from straight horizontal. And my acceleration, some students do all this, they ask for the acceleration, so they do the vector collectors, get the force, and go on to the next question. But you can't do that. The question asks for the acceleration. So it's the net force over the mass, so 92.93 divided by 90. Now that mass isn't just of the kid, it's of the kid and the toboggan together. So that's 1.03 meters per second squared east, 4.18 degrees north. That's another thing I sometimes see kids do. They get the acceleration, they're at 1.03 meters per second squared, but they don't give the angle. If you don't give the angle, it's wrong. Remember, acceleration is a vector. Force is a vector. Okay? Here's an example where we have a vehicle 2,000 kilograms and you have two forces pushing 320 newtons each way, 15 degrees from the horizontal. So my horizontal component is going to reinforce. My vertical components will cancel out, right? If you want to start doing some shortcuts. But let's not do any shortcuts. My x component would be 320. So we can say, what about friction, all that? Well, I'm not worried about that right now. Assume friction is not important yet. We'll get to that where it will be. 320 cos 15 is my x. 320 cos 15 is my x for F2. So they'll add together and they become 618.19. My y component, 320 sine 15 going up, minus 320 sine 15 going down. So the y is 0. So my acceleration is 618.19 divided by 2,000. The object is moving at an acceleration of 0.31 meters per second squared to the east. In your mini text, there's some examples for you to try, and there they're listed. So you give that a shot. And let's talk about one more topic here, which is known as static equilibrium. So here we go. Static equilibrium is when the net force is 0. When you add things together and you get a net force of 0. So there is no acceleration. Where would we find things like static equilibrium? Hanging a picture, hanging a flat screen TV from the wall, right? You don't want that to move around. You want it to be mounted properly, mounting any sign. You want to S-I-G-N, right? Not S-I-N-E. You don't want there to be an acceleration. So you want to have the tensions in the ropes and the wires, everything to cancel out so you don't have an acceleration. That's what static equilibrium is. That's important in sports, important in dance, ballet. Talk about static equilibrium, all sorts of things. So suppose here I'm taking a picture and frame together. It's 5 kilograms. So the weight, I hope you remember what weight is. Weight is the force of gravity. It's m times the acceleration due to gravity, and I'll assume I'm on the surface of the Earth. So it's 5 times 9.8 in our example, which is 49 newtons. So I have a weight of 49 newtons going down, and I have two ropes. I'll assume they're the same material in each rope, and they're 30 degrees mounted from the horizontal. So we want to get that tension, the tightness in the string, how taut they are. We don't want it to be too taut because then it would snap and your picture would fall to the ground or your TV would fall to the ground, and that wouldn't be very good. Unless you're watching a lousy TV show, then you wouldn't care. So my x direction, F1, is going to be F1 cos 30, and y direction, F1 sine 30. For the second wire, I'm going in the negative x, so it's negative F2 cos 30, and my y is F2 sine 30. So they're both pointed up. Force of gravity in the x direction is 0, but y direction, that's my weight. That's going downwards, that's minus 49. Now, for static equilibrium, my x component and my y component both have to be 0. So now let's look. So F1 cos 30 plus negative F2 cos 30 is 0, which means F1 cos 30 minus F2 cos 30 is 0, which just means F1 equals F2. So in the symmetry there, the F1 and F2 are the same, and that's all that tells you. Okay, if it's not symmetrical, it's a bit more complicated. Maybe we'll look at that later. But for now, F1 and F2 are the same, and that's all the x component data tells us. They have the same tensions. The y, well, sine 30 is a half, so 0.5 F1 plus 0.5. Well, I know that F2 is the same as F1, so I can substitute in F2 equaling F1. So 0.5 F1 plus 0.5 F1 plus negative 49 equals 0. So F1 equals 49 newtons. I don't know why it said that there. F1 equals 49 newtons. F2 equals 49 newtons as well. Oh, I think that was supposed to say F2, not 42. So F1 and F2 are 49 newtons, so the tension is the same. If I switch to a larger mass object, 10 kilograms, then the force of gravity would be 98 newtons. So there'd be greater tension. Would there really? Yeah, because you'd have F1 minus 98 equals 0, so F1 equals F2 equals 98 newtons. So that would make sense, right? A more massive picture is going to cause a greater tension in the wires. So you better make sure that the material that the wires, supporting wires, mounting wires are made of have to withstand that force. If they don't, then you're going to have a mess. The third one, I go back to 5 kilograms, but I change the angle. I make the angle more, let's see, would that be shallow or, well, I just change it to 10 degrees. Whether you want to call that shallow or not, let's not bother with that. Let's just say it's 10 degrees. So it's looking more horizontal-like. So again, the x's cancel because I'm using the same angle on either side. So I'm just focusing on the y, and you end up with 141 newtons for the tension. So the strings are getting more tense for the same mass if you make the angle closer to 0. Okay, it's not sagging as much. That's one way to do it. It's more stretched tightly across. If we go in the other direction where we make it almost like it's one rope, right, 89.9 degrees, then the tension is just 24.5 newtons. So that's essentially this lowest tension you can have. Okay, but it might not look very good, but it won't be very tense if you have the two ropes, which are with a theta of 89.9 degrees. And if you find a good video on hanging a picture, email it to me, right? How hanging pictures in art galleries relates to tension. Send me an email. That'll be interesting. We could then watch that one together. Okay, this next one is at an angle different, and you can try that one on your own. Okay, has a more fun one. Force of gravity, well, I don't want to bring you down with another topic for today, or this lecture. This lecture might be more than one day. Who knows how it's all going to work, but that was the lecture. So I'm going to go have a Fig Newton now, because that's a good thing to have. Okay, have fun. Try all those questions.